Hey, John here. Let's look at the standard template library list container. Now I'm going to talk about this a little bit in contrast to the vector container, since we already talked about that, okay? So hopefully this will go a little bit faster, and it will also reinforce this idea of the common API that the standard containers have in the standard template library, okay? So let's see what we got to do here. Obviously, the first thing you need to do is include the list header file and bring the list into your namespace if you want to use the short form of referring to the template like this. All right, so let's do a simple little program. I'm going to create a list of integers. I'm going to call it L. I'm going to put 5 elements in that list, and we've seen pushback before when we were talking about the vector. It works the same way with the list. We've seen a range-based for loop before. When we were playing with the vector again, it works the same as it does with the linked list. Again, this common theme of all the template containers having some basic shared functionality to allow your code to have a similar feel. So once you learn one or two of these things, the rest of them are somewhat intuitive. You don't have to start from scratch every time, which is a beautiful thing. As your career goes on, you will appreciate this very much so when people have this forward vision in mind when they create stuff that is designed to all fit together. All right. What's going on down here with this loop? We'll talk about this in a minute after we watch how the rest of this runs, okay? So I hope that this is pretty darn obvious, right? You're going to iterate over all the elements in L one at a time, setting E to refer to each element one at a time so we can just print it out like this, okay? And then we print a blank line after the end. So what are we doing here? We're putting 0 through 4, right? That's less than 5. Into this list, and we're pushing them onto the back so they'll go in that order, and then I'm going to just print it out. Let's see how this thing works. Okay, let's compile it up. Now let's run it. And there's no shock there. It printed it out 1, 2, 3, 4. Let's look at how I printed this one out down here just as a little side note. Notice I put commas between the values, and there's not an extra comma over here. There's not extra blanks over here. There's not extra blanks at the beginning of the line. It's not formatted in a mess. Like, in a way, this one here could be considered messy if you didn't want these spaces over here. Or I also didn't put spaces at the end on the right there, okay? So let's look and see how this loop works down here to make sure that I didn't have that extra comma. Look what I did here. I said, give me a variable called pause and set it equal to the begin method from the list container, and that's going to give you the same thing it did when we got one from the vector, which is an iterator that represents the position of the first element in the list, okay? And I use auto here because I don't want to deal with putting the giant definition of what this thing really is in here. It's very handy. We talk about that in the vector video. So I'm going to say, well, my iterator that I'm going to use to propagate through the linked list is not equal to end, right? You remember how the begin and end work. If this were the representation of all the elements in my linked list or in a vector or something like that, remember begin represents an iterator that is pointing at the very first element that is in the container, and end represents this element that would be the next one if it exists, right? It points to the element that's past the last real one, which would be right here, okay? So what is going on here? Start where the begin iterator points, and if you ever reach where the end one points, you know that pause is pointing at something that does not exist anymore. So simple little loop. Start at the beginning, and while it's not equal to I ran off the end, do this. Now, so you can see closely at what's going on in here. Write to standard out, and I ask, is position not equal to the begin? Is this any element that's not the first element in the list? If that is true, I print this string here, which is the comma that goes between the elements. All right. When pause is equal to the begin, this expression is false, and the value of this entire expression in parentheses here is a string with no characters in it. Okay. So this is the key to printing those commas and not having too many and not putting junk at the beginning of the list or on the end of the list, this little expression right here, okay? And then to print out each one of the values, you simply dereference the iterator, which is what you can do this with any container. That's what one of the things iterators are for. And once you're done dereferencing it and formatting it and printing it to standard out, we then increment it by 1 over here, right? So there's a lot going on in one line of code right here. All right, so this is going to loop through each one of those elements, print the values out with commas in between where appropriate, okay? And when it's done doing all that, it prints the end of the line, and we go on our merry way, and you can see that's what happened in there, all right? So just a little side note, if you have to put commas between them and do it right, that's one way to do it, okay? Now let's make a little change in here just for fun and let's see what happens here. Now you'll notice that I did include the vector class and brought it into my namespace as well, but we're not using vectors anywhere. I did that so I can do this. Now this is one of the nice things about a standard container class. As long as you're not doing anything too esoteric that's specific to any one container in contrast to any other, these are truly interchangeable. And we'll see that right now. This will compile and it'll run and it'll give us the exact same output, all right? Now, you might think, why bother having 2 containers if I can do this sort of thing? Well, you'll see that some containers are better at certain kind of operations, while others are better at different ones, okay? This just so happens to be a pretty trivial example that certainly the list and vector containers can both do as is. So these 2 containers, the list and the vector, are very compatible in that they both provide all the same kind of behavior with these types of iterators and the pushback routine. So let's look at another example. We start out the same sort of thing going on here. We got a list. We put 5 elements in there, 0 through 4, right? And now what are we doing? We're going to look at the first element, the front element, and then we're going to do this. Okay, now I didn't show this when we were talking about vectors. You can do this with a vector as well. And what do we do down here? We print them out the same way we did before. So the only difference between the insert 0 example and this example here called insert 01 down here is I want to demonstrate how front can be used. And the thing about this front method, this actually does not return the value of the first thing in the list. It returns a reference to the value that is the first thing in this list. And that subtle difference is I can use this on the left side of an equals, all right? I can assign the 9 to replace the first element in the container, all right? So what are we going to do? We're going to fill it up. I'm going to print out, here's the front element, then I'm going to change it to a 9, print it out again, and go on my merry way, okay? So let's see what happens here. I want to run insert 1, not insert 0. Okay, so first it's 0, it changes it to a 9, and then I print out all the elements just like we did see a minute ago. So that should make sense, right? Because I've replaced the front element with a 9, all right? I just wanted you to see this notation before we move on. Now, the subtlety of this in the documentation, all right? If we go over to cppreference.com here, this is actually laid out a little bit more friendly for video, so I think I'm going to use this site today. Let's look at the front. Oh, I just had it on the screen right here. This is the method for the front, and if you look at how it's defined, it returns a reference, okay? Return a reference to the first element in the container, all right? Now, this is what allows us to do that assignment, okay? If you put front on the right side of an equals, an assignment operator, all right? Let's do that. In fact, one could argue I did here, right? When I'm not assigning it to anything, but I'm printing it out, okay? I can use L front to see the value of the thing that's at the front of the list, and I can also use it to assign a new value to it, all right? This is what I wanted you to understand, that little subtle side note right there, okay? Now, before we get any further into this, let's do a side-by-side kind of compare and contrast between the standard list and the standard vector here, all right? This tab here is on the vector page, and this tab here is on the list page, all right? So let's switch back and forth and have a look-see at a couple of these things. All right. So here's the declaration of what a list really is. It's a template class that has, this is the type that you specify, like int or whatever. This down here is beyond this lecture. This is so that you can actually provide your own memory management system to allocate and deallocate the nodes for your container if you want. Okay. And this, of course, is another kind of allocator. Again, beyond this discussion, we're going to keep to the simple ones here today. Now, the key here is that the list container is implemented as a doubly linked list. All right. Now, we talked about singly linked lists, doubly linked lists. It turns out if you want to, you can also look at another kind of a list that has a standard container called the forward list. And that is a singly linked list. And they point out the obvious that if you have a doubly linked list, you can iterate and traverse that list, sometimes we say, in either direction. Okay, go front to back, back to front. But in a singly linked list, the forward list can only go forward. That's actually why they call it a forward list. So we got two types of lists is my point. You got doubly linked, singly linked. We're talking about the doubly linked ones. Their generic list is doubly linked, all right? They added forward list as an afterthought as an optimization when a singly linked list would do. Now we see the various members that are inside this class that define how the class is used and how it works. And you'll see this is very much looks the same as the vector does. So let's look at the vector over here. A quick recap that these are actually stored contiguously in memory and in an array, an actual array inside of the vector class. And they point out that they can then be accessed through iterators or also by directly accessing them, okay? And by that I mean you can use the square brackets and the @ member. You get direct random access to any element you want in the vector. This is the vector class we're looking at right here, okay? Now, let's see what happens in terms of the member functions that compare and contrast to the list. What do we got? You can construct it. You can assign things to it. You can this is the allocator that we're not talking about for the advanced stuff. The same kind of things, all right? And assign in a vector, you usually give it like an, what do they got? A count and a value. If you look at the assign in a list, it'll do the same sort of thing, count and value. We talked about how you can use this sort of thing in a vector when we were talking about the vector. And it works the same way with the list. And of course, this website gives you a couple of examples. This example is a little bit fancy because they're using a lambda right here. We haven't talked about that yet, so I won't go into the details. Let's look down here. Element access. I can get the first or the last element directly by using front and back. And this is the linked list template page we're looking at right now. Okay, and this makes perfect sense. If you have doubly linked lists, you've got your head pointer and your tail pointer in there. So sure, I can get the front and back easily with directly accessing them. Now, you can do the same thing with the vector. And like I said, you can also get any one you want by saying, I want number 8 or I want number 7, of all of the elements that might be in the vector. So this is a benefit of the vector has over the linked list. If you want number 8 in a linked list, you have to go to the beginning using one of these iterators and then move forward, 7 elements past the first one to get to the 8th one, right? I mean, that just makes sense because it's a linked list. So what else do we have? We got empty and we got size, and down here, the vector has the same iterators. We got empty, size. Now the vector has some other things that you're going to have to deal with. Okay, due to the nature of a vector in that it has an actual array in there, this notion of the reserve and the capacity and stuff like that, and shrinking the thing to fit and stuff like that, this is all very specific to just vectors, all right? The max size, they both should have a max size. Yes, they do. This has to do with, the capability of your system, or in this case, the system library. In theory, how many could fit if you just kept putting stuff in here, right? That's what max size is for. All right, back on the list page here. We can clear all the elements. We can insert new elements. We'll talk about in place in some other lecture. This is an optimization for constructing and putting things into the list simultaneously to save CPU time. It's a neat thing. They added it, looks like 10 years ago. Again, that's worthy of a tutorial on its own. I can erase individual elements. I can do the pushback, and again, the optimized version. And I can pop the back. These two things, all this stuff is the same as it was with the vector, the same behavior. Insert, erase, pushback, pop back, resize, and swap. This is, of course, for the vector, right? Now let's look at the linked list here. We got a little bit extra going on here. Why do we have extra? This is a big deal for linked lists. So you got pushback and pop back. All this stuff here is the same as a vector, and we've already talked about all that. The resize here is also the same as a vector, okay? Swap, I don't know if I talked about that or not. This does not swap elements in the container. This swaps the entire contents of the container with another container, all right? Personally, I don't see a lot of use for this, but they provide a way to do this. There's probably some standard library function that wants to do this sort of thing. Again, now I'm on the vector page, and you can see it too has a swap. And again, it means it's swapping the entire contents, all the elements of one container with that of a different container. There's another swap function that allows you to move elements around within a container. All right, so don't confuse the two. That's why I wanted to beat that a little bit in this dialogue. So what's up with push front and pop front? All right, how come? This is the linked list version here, standard list. What's this all about? Well, let's look at push front. I think you can guess that push front is kind of the opposite of push back. This one prepends the given element value, right? So it takes a parameter, just like the pushback does. It says put that value in this container. In this case, we're talking about a list, and put it at the beginning of the container. Make that the new beginning of the container. All right. Look at this particular website. Includes a little section called complexity. All right. We've talked about big O notation and complexity. This runs in order one time. It's constant. No matter how big the list is, I can prepend something to the front of my list in order one time. That's valuable, all right? Because, first of all, a vector doesn't let you do it at all. It doesn't even give you a function. Let's take another closer look on the insert function, all right? We're looking at the vector right now. Standard vector, insert. And why did I jump onto this? Because this is very much like push front. Because when you do insert, you can tell it where to put it. And you give it a value. You can have other ways of inserting things too. These are just variations on a theme. The simplest of terms. Here's the position where I want you to put the thing, and here's the value I want you to put there. If I use begin as the position, insert will act like push front. Okay? In fact, I suspect that push front is literally implemented this way in the linked list. Now, why didn't they do this for a vector? Well, it's because of this complexity. Look at the complexity in the vector when it discusses how insert works. Right? It turns out the complexity itself is complicated. All right, now let's look at the list insert. So we do apples to apples. Here's the list page, and here's the list insert, right? We see it as the same function signature right here. At this position, put this value. And specifically, it means that the value is going to go before that position that it gives you, okay? Now let's look at the complexity of this. Okay, there's something going on here. It's constant. It's linear in count, it's linear in distance, it's linear in size. What's all that about? Well, notice you got 1, 2, 3, 4, 5, okay? These numbers here on this particular website refer to the variations here. Here's variation number 1, variation number 2, 3, 4, and 5. Now, it turns out that variants 3, 4, and 5 tell you I want to put a lot of them in there, right? This is like at this position, put 20 of these values. Well, it should make sense that that can't run in order one time. That probably runs in order 20 times because this count tells you how many to do. So if we look at variant number 3 and we look at the complexity down here, it says it's linear in count, which makes perfect sense. If count is 5, it takes 5 times longer than if than it does to do 1. All right. Now let's look at the vector one over here. All right, there's the vector page, and here's the vectors insert and the complexity statements here. So it's constant in the simple case, plus it's linear in the distance between pause and the end of the container. Now let's think about this for a minute. All right, we're looking at the standard vector insert routine here. And if I say at position X, I want you to put this value in there, what does the vector have to do that the linked list does not have to do? Now let's look at our generic representation of a container again here. If this is a vector, and remember this all started when I was talking about, push front. So if I have a vector and I say, where's my insert routine? I use this right here. I say insert at position begin and put a value in that vector. What does it have to do to make that happen? Well, if this is a vector and I want to put something at the beginning of this vector, I can't just stick it over here on the left and build to the left because the contents of a vector is stored in an array. And this is the first element in that array. So I got to make a hole here to put the new value in there. How do I do that? I have to move every one of these over. I have to move this value over to here and extend the end over to the right. Then I have to move this one to here. Then I have to move this one here to there, and then this one to there. And I have to ripple all these to the right by 1, which will leave a hole on the left here, and I can put the new value in there. Okay? That is what is necessary if I push something into the beginning, or I say insert something at the beginning location into a vector. This is not a particularly efficient thing to do if you use a vector as your container. And that's what it says down here in the complexity, right? Oh, it takes constant time to get the element into the container. Once you have a place to put it is kind of what they're talking about here. Okay, now you can see these other ones have to do with what are you doing when you have more than one, right? Just like when we were talking about the list, some of these allow you to say put count number of elements in there, right? Where is it? Like here. So it might be linear plus count times, right? So this is like variation number 3. So if you go down to complexity again, linear in count plus linear in the distance between pause and end of the container. And as I just discussed, if the distance between pause and the end of the container is far, you have all this rippling to make a hole, right? But if the position is way over here, let's say I say insert into this vector at end. Well, it puts it right there, moves end over to the right by 1. It does that in order 1 time, and we're done. So a vector is great, provided that you're only adding things to the end. And it's also great if you're only removing things on the end. So if you do push back and pop back to change the contents, the number of elements, I should say, in a vector, you're fine. That always runs pretty much in linear time. Yeah, it might have to, on occasion, reach over and reallocate some place, right? It might have to call reserve and change its capacity, right? Because we talked about that before. A linked list never has to worry about its reserve and its capacity because the nodes in a linked list can be stored anywhere in the memory of the machine. Therefore, adding things to the front of a linked list, right, which is what we're looking at here, is the linked list insert. It doesn't matter where the position is. It'll always run in constant order 1 time, okay? Because all you do in a linked list is readjust the links. You don't move anything physically anywhere, All right, so what is the benefit then in a linked list? Well, if you have a dynamic bunch of activity going on, if these were to represent the nodes in a linked list and I want to put a new node between these two, I don't have to move all of them around. I can just change the links that connect these together and shoehorn in another node down here and leave everyone else in memory where they currently lie. All right, so that's why we have these different containers. The question becomes, what do you do with the container as it starts to fill up? Do you insert and delete things in the middle of your container? Well, you might want to ask, should I use a linked list rather than a vector, because the linked list could be faster. But of course, that is only true if you can get your iterators to point to where you want to insert and delete them, right? Notice the insert does not have a function in here that says, at position such and so, using like the square bracket notation, or a number that just simply says at this position 5, put this in here. You don't have that ability. You have to get an iterator to point to the place where you want it to go. All right? That sometimes can require more effort than you want to as well, especially if you don't do it very often. I'm going to close all these extra windows so I don't get confused. Right, so this is the vector page. Remember the second tab. Let's go back to the top, make sure. This is the standard vector. This one here is the standard list, all right? So let's move on, all right? So what's the benefit of the list over the vector? If you have a lot of dynamic activity in the middle of your list, you're doing better than the dynamic activity in the middle of a vector. And by I mean activity, I'm talking about inserting and deleting in terms of how much time it takes the computer to actually do that work. If you want to push things onto the front of your container, you're better off with a linked list than you are with a vector, because the push front and pop front can run in order one time in the list container, right? Constant complexity. All right, now you know why we talked about complexity before. Resize. This is kind of an interesting thing to me. I never think about linked lists in terms of resizing them, but this has the same behavior as it does with the vector. All right. Now they added this just so that the containers all look and feel the same. So I can do a resize if I want to. All right. What does it mean to resize, to shrink the size? Well, that makes sense. It just prunes off all the stuff at the end of the linked list. Right? If my linked list has 10 elements and I say resize it to 5, it'll delete and erase the last 5 elements and shrink the size of my list down. If the current size is small and I say make it bigger, this is the thing that kind of is strange to me in a linked list. But sure, you can do that. What does it mean? If it's currently 5 and I say resize it to 10, well, what'll happen is these new 5 elements will be added and their default values will be used, okay? Now, it might be obvious that if it's a list of integers, then they'll all be set to 0 or something like that. Now, the reason they freeze it this way is because what if it's a list of some classes that I invent myself? Say I invent a new class called XYZ, and I have a list of those XYZ classes. And I say change the size and put more of them in there. Well, what the heck is it supposed to do? Well, that means it will create 5 more XYZ class objects by using the default constructor. All right? That's why they phrase it this way. Now we have these operations here. These are somewhat, some of these are unique to linked lists. The merge and the splice are very much so unique to linked lists. Now, where the vector is concerned, the vector-specific kind of functions are buried in the management of its capacity here, all right? So these things here are kind of unique to vectors. Well, they are unique to vectors. Shrinking, the capacity, the reserve, we talked about that before. In a linked list, the things that are kind of unique to just linked lists are these things down here, and that is this merge and splice, all right? These two have a very similar sort of thing. What does it mean to merge 2 linked lists? Well, aren't you kind of like moving elements from one to the other? Let's look and see a little bit about what merge is, okay? Merge. It's a member function on your list that you can give it as an argument another list container. merges two sorted lists into one. And this is the key for the merge. Your lists are sorted. So what happens is you take two sorted lists and you merge this other list into a list. The combined giant list is still sorted. Okay? And they should be sorted in ascending order before you do this. Okay? Now, because we're dealing with a linked list, it says that no elements are actually copied. In other words, the copy constructors of the elements in the list are not called. This is a huge benefit, especially if those objects in the list are complicated, use up a lot of memory, have a lot of pointers in there, right? They might have to use deep copies and things like that in order to get them moved from one place to another. But that is not needed in a linked list, okay? Because they're simply relinked in order to be put from one list into the other list, all right? Now it says the other list, right, the source of the merge. We're going to pilfer all the nodes out of this list and merge them into the list that you called merge on, okay? The other list is drained, right? We're going to steal all the elements out of that, right? Now, this website has this kind of neat little thingy down here where they give you these little example programs, and you can actually run them right in the website if you really want to. What's going on with this thing? He actually has an overloaded insertion operator to print his lists. And so he can create two lists here. These are obviously not sorted. He then sorts the two, prints out the two lists that are sorted. Then he merges list 2 into list 1, and that's how you do that, right? And then they print out the merged list down here. So this is obviously what they're trying to do here. So if we want to, we can actually edit and run this code if we really want to, okay? So here, now I can edit this. So let's break it. Let's see what happens if we have the same element in here twice, right? Let's put 9 in both of these. What happens here? This is the first thing I like to think of. When I look at an example like this, I'm like, come on. Show me what happens if I got the same one there in there twice. In other words, are the duplicates removed? I don't know. And what happens if you have like a collision, we might say, in this scenario? So I said, all right, fine, let's go ahead and run this one. Now it's actually going to compile it on the website, and then it's going to update my output. It went really quick. Look, there's my 2 9s. So that answers your question right there. Presumably, you asked the same one I did, which was what happens if both lists have the same value. Well, it keeps them. All right, so you could make some observations that the merged list, the number of elements in the merged list is equal to the total number of elements that was in list 1 plus the total number of elements that was in list 2 before the merge, okay? The total number of elements left in list number 2 after the merge is 0, okay? And we can prove that by repeating this line of code here. If they probably should have done this in their example, in my opinion. Anyway, so let's print out list 1, list 2, the merged list 1, and then print out list 2 a second time. Let's see if their little printer outer here is any good. It looks like it's pretty decent. In other words, does it work correctly if the list itself is empty? All right. So let's go ahead and run this. And you can see now that the list 2 is emptied. Now let's look at this line of code I just noticed right here. They said auto ampersand I. Their arrange-based for loop here looks different than mine. I just learned something here. This is a very good idea, okay? There's something subtle going on here. By declaring I as a reference rather than the value of each one of the elements in this list, this will run more efficiently than my example that I used when I printed out my elements down here. And the reason is because I declared a variable that gets assigned a copy of the value of each element while this iterates over the list. Okay, if I put this in here, what I do is E is set to refer to the elements as we traverse this linked list, which means they're not copied in order to execute this loop here. That's kind of a subtle thing, but these are the kind of efficiencies that you want in your code. Let's make sure that I'm right and that it still works. Of course it will. It just makes sense. I just didn't think about that. These are the sort of things that can get you into a lot of trouble when it comes to efficiency. And I'm embarrassed to just say that I didn't notice that in my own little example program. Okay, it's not a problem down here because I'm dereferencing these iterators directly, and those are themselves essentially the same kind of thing as a reference is like this when this is running. Okay, so yeah, we're all learning something from these little examples, right? A good reason to go back and review them from time to time. All right, so that's what a merge does on a linked list. And that is in stark contrast to a splice, all right? Now, a splice, just like if you've ever, well, I don't know how many of you actually edited real movie film before in your life, but you actually cut up physical strips of film between the frames and you tape them together. And that's what splicing is, and that's exactly what happens in the linked list. I'll give you all these variations. I can splice a whole list onto an existing list, and I can say put it and start it, at any position I want. Or I can use iterators and copy a range of elements from one list into another, these various variations. I'll leave that as a task to the viewer to decide which one is the most appropriate in any given situation. The beauty here and the point is you have a lot of variations to decide exactly how you want to do this splice. Do you just want to put it on the end, take one whole list and stick it on the end of another? That's easy. You just specify end for the position in the target list, and you just take the whole list from the source, the other list that you're grabbing. Okay, and again, you're going to steal all the elements out of this other list, and you're going to put them somewhere in your list that's going to accumulate them all, right? Okay, so we look through here, and that will be confirmed by this statement right here. Transfers the elements from the other list into this, and this is their way of referring to the list that is the target. So star this is the list whose member function is being called, right? Elements are inserted before the element that is pointed to by pause. So you can actually set pause to begin if you wanted to, or end, which would mean you prepend or postpend the source list into the current list, right? And the other list, the source, becomes empty. You've stolen them all, right? And this statement here is kind of interesting. If you try to copy a list into itself, the behavior is undefined, right? They're not going to help you to do prevent you from doing incredibly idiotic things. They're going to just simply say your program's probably going to crash if you try to do that. So don't do things like that, okay? And again, these 1, 2s, and 3s are going to refer to these footnotes over here. And as such, what you're going to see is that, you've got this first and last iterator over here. So this means you can take a range of elements from this other list. I don't want the whole one, maybe. I only want, 10 elements, starting at this iterator and ending at that iterator that refer into this other list that you're grabbing elements out of, all right? So they're going to talk about how all that works. In our favorite half-open range, right? From first, including the first, up to last, but not including the last. This sort of thing is great fodder for quizzes. This is where your quiz questions are going to come from if you're taking a class that covers these topics. Understand the open range, okay? And this matches perfectly this concept here. If you say begin to end, you want a half-open range because you want everything starting at begin, including begin, and up to, but not including this end over here. Because if you included the end, you're copying this illegal, non-existent, there's nothing here element over here, right? So all this is thematic, okay? That's what's going on here. You want that, okay? What do we got going on here? Complexity, again, it's constant for versions 1 and 2. Why would it be constant and not linear, right? Remember, we're dealing with a linked list. What does it mean to take all the elements from one list and stick them in another? It means you're going to link into your target list. Let's say we want to put them on the end of the target list in the easy case. Splice it onto the end of an existing list. All you're going to do is take the last element in the existing list and point its next pointer over to the first element in this list. And then hook the backwards pointer up back into the target list. Now you're going to reach over into this source list and you're going to set its, element count to 0 and disconnect its head and tail pointers and so on. But this all happens in order one time because it doesn't matter how many elements you just transferred is the point. The source list could have 1 million elements in it. And all you need to do is hook the last element up of the target list up to the first element of the source list. And you're done. Okay? No matter how many there are. That's why the complexity here runs in constant time. Now, if you were to try to do an operation like this in a vector, which, by the way, doesn't even include a splice method, but you could write your own if you really think about it, what does it really mean? If you wanted to copy all the elements from one vector into the end of another vector, I could iterate across the source vector and call pushback on the target vector in a loop. And then when I'm done with all that, I could go back to the source list, or source vector, I should say, and I could clear it out. Right here, I call the clear. This is, again, the vector page, right? So this would have the same effect. But if you think about it, that would run in linear time because I'd have to literally push back each one of them one at a time. I might even have to grow the capacity while it's going and stuff like that if I did the same kind of an operation on a vector. So the linked list wins in that category. All right? I can do a splice and I can do it in order one time in a linked list, and I cannot do that in a vector. And that's why they actually provide these as, I would argue, these are hints, okay? This is probably efficient, okay, if they provide a way to do it. If they don't provide a way to do it, then, well, you're kind of on your own and you're going to invent something that might not run very quickly. Now, that's not to say you must use a linked list if you want to do these operations. If you have a program that runs for 6 months and it only does a splice or a merge once or twice while it's initializing itself and then never again, I would argue, who cares if I used a vector or something like that? So let's say you got an app that does configure itself by doing merging and splicing. You might even want to push stuff into the front of the list or insert them in weird and awkward ways where a vector, this is the vector over here, would be inefficient at doing that. But once that has been completed, like during the startup of your program, or in extremely rare situations over the long course of time, and then after that, you spend hundreds of millions of times using this operator here, or the @ to get random direct access to all the elements in a vector by their index number, you might still want to use a vector anyway. Because the bulk of the time, the question becomes, are you spending all your time using the direct access methods, or are you spending all your time trying to, insert and push front and merge and splice or even sorting and things like that on a container where a linked list might be a better choice, okay? So the question is, how often do you do it? How hard is it on the machine when it takes place? And, where do you spend the majority of your time in your application? This is the kind of thing that goes into deciding which kind of container to use, all right? So that's a compare and contrast between the list container and the vector container. Some insight into which one might be better suited for different types of applications. Let's look at one little last example here before we wrap this up. Let's look at the same kind of a thing. We've seen this before, but let's look at a variation on how these templates really work. I'm creating a list of integers called L. I'm going to put the same 0 through 4 in them 5 elements total. And I'm going to print it out using 2 different techniques here. All right. Now, we've seen this first one kind of thing before. I wrote early on talking about containers in general. And I wrote I wrote a template class that's similar to this one that iterated over the elements of a vector. Now, look at this one here very closely. This template function uses a type here that is never used again down in here for anything, okay? Other than when it actually prints out the value here, the type of I is determined by the type of the thing that is in this container here. This is very abstract here, all right? So what this is designed to do is print the elements of this list. In fact, I shouldn't have called it list because, as we'll see, it doesn't matter what kind of container this is. Okay? This is going to print the elements of any container, not just a list. And that's the key here. Before I showed you how to print the elements of a vector, and I wrote a vector-specific template that worked fine, and I could use it on any kind of vectors, of doubles and integers and so on. No matter what kind of vector, that code would always do the right thing and format the output accordingly. This one, I didn't even mention the kind of container. Okay, this will work for lists as well as vectors, as well as some other kinds of containers, provided that I can use a range-based for loop with the container. All right, so this is good for all containers. This is the key. All right, we now made another big leap forward in what it means to create a template function and apply it to the standard template library of containers. Okay, so now I have one that works for all containers. I don't have to rewrite this all the time. This one's a little more explicit with the if then else and so on here. Here's another one that'll apply to just about any container as well. Okay, let's look at the differences between these two things. What does the top one require? Well, the top one says give me, in fact, this should be a reference. This is terrible. Yikes. And not only that, it should be const. Boy, am I getting sloppy. It's early in the day. So what I have here is a reference to a container that I want to iterate across and print out all of its elements, all right? Now, it'll work if you don't have const and if you don't use a reference, but what it'll do is it'll require more complexity when your program runs, because it'll have to make a copy of the entire container if you ask it to do so. By putting a reference in here, it won't make a copy of the container. By declaring this const, you're guaranteeing to anyone who calls this that you're not going to modify the elements in this container. All right, so this is just this is better behaved. All right, but the behavior will be the same either way. All right. Okay. So what's the difference here? This one's going to go through one at a time, grab the values and print them out. And if it's the first time through, it's going to do what? It's going to change this variable. So what's going on here? I start out by creating this thing called sep, which to me means separator. And I set this to an empty string, no characters in the string. And I got a Boolean flag that's set to true. So what I do is I print, to standard out, I print the sep, which is nothing, followed by the value. And then I say, if this is the first time through the loop, change sep to this thing with a comma so that all the other ones have a comma that comes before them. And set first to false so I don't have to keep redoing this every time through the loop. And that's what's going to put commas before all but the first element and get the right number of commas in that print line. All right, so that's how this thing works here. What's the one down here do? This one also will work on any container, provided that it has a begin and end, and provided that it has iterators that you can add one, what we call a forward iterator that can, advance through the container. So what's going on here? I have a first and I have a last. Now this is this open-ended range. I created a template function here that takes an open-ended range of iterators. Notice I'm not asking for a container. And what do? I say pos equals first, while pos is not equal to the last. Print it out. We already talked about the question mark operator and how to do this and print the commas correctly. And then I print out the value that I'm iterating over, and I advance that iterator to the next one. This whole code is basically the same as we saw earlier on in this video, okay? Much shorter, maybe easier to understand. I don't know. Sometimes when I look at code like this up here, there's so much going on. I actually have to look at it all. And there, and there's a Boolean. This takes a little bit longer for me to interpret than this one down here. I'm comfortable looking at code that has the ternary operator in it. If you're not, then this might be more awkward for you than the first one. Okay, but to me, this is a lot more concise and accurate and clear. And it doesn't require knowledge of containers at all. It just has to deal with these iterators. Okay, this prints out the entire container that's been passed in. This can print out any open-ended range. Okay, so this actually has more functionality. Now, we're not going to use it in this particular example. Here, I'm going to just say, print out all the elements of this list called L. And as you saw a minute ago, I renamed this to container because it works on other things as well. And we'll see that in a minute. I'll change this to a vector is my point, and we'll see it still works. And then the print iterator also will work regardless of the kind of container, because it doesn't even refer to the container when it runs. It only deals with the iterators themselves. Okay, so let's go ahead and compile this up and run it, and we'll see that it works just fine and dandy. Both of these print out the exact same results with all the commas in the right place and no extra comma at the end, no comma in the beginning, and formatting your output in a useful and sane manner. Now, what happens if I don't want to print the whole list out? All right, so let's change this and make our list not be the entire contents, but just part of the contents in some open-ended range like this. Let's say IT equals, oops, I want to paste it up there. I want to paste it over here. And then what do I want to do? I could say plus IT to move it over an element, plus IT. So I moved it, over twice here. All right. Now remember, this is an open-ended range down here. So by sending it equal to begin, it will print nothing at all. By adding 1 to it, it'll print 1 element. By adding 2 to it, it'll print 2 elements, and so on, right? Because this is going to represent the very last one plus 1. So if I start with the begin and I end with the begin, then first equals last, it'll print nothing, okay? If the last is the begin plus 1, it won't be equal to last the first time through. It'll just do one of them, all right? So this will actually print 2. All right, and there you got that. Now, you can't, of course, do that with the first printer because it takes the whole container, all right? Now, as I said before, we can change this to a vector. Oops. And up here, in order to do that, of course, we have to include the vector class. Recompile that, and it'll still work, okay? Of course it'll still work, because these template functions up here will accept anything as long as I have an iterator. And it doesn't care what kind of object the iterators point to, or refer to, I should say. And this container printer up here doesn't care what kind of container is being passed in here, as long as I can create this range-based for loop based on that container. And that is the power in itself, because this function, once written, will apply to anything. I reuse it in my code over and over and over again. I don't have to write 1,000 different print iterator functions or print functions that work on every different kind of container and every kind of data type. I do it once and I never do it again. Your programs are smaller and more concise. They're more abstract, yes, and maybe it takes another minute or two to really think about what this does because it doesn't have a concrete type in here. But doing things in the abstract allows them to be applied in more different cases and situations. So thanks for watching. See you next time.